You ready?
Okay. Good afternoon, everyone. So the next speaker is Professor Jose Antonio Langa. Professor Jose Antonio Langa is full professor at the University of Seville. He's a well-known mathematician in dynamical system. He have a lot of publication and citation. And today he's gonna talk about attractor as information fields application to cascade system. So Jose Antonio, thank you very much for accepting our invitation, and you have the word.
Okay, thank you very much for the invitation, Diego, Juan, and the other organizers of these seminars. Thank you for all the work on not of especially of this seminar, but all the seminars in the series. And in particular, thank you very much to Professor Murat for this very interesting talk he has just given to us. So I'm going to talk on a very different of a very different subject. I'm going to talk on attractors. Most of you or many of you know this concept, but I would like to start revisiting the concept of attractor because I think there are things that we should put some attention before going to some applications. From so I've split this talk in three parts. This one is just going again to the concept of a global attractor so that we can see this object, this mathematical object, as a new concept, more relation to information theory. Intrinsic information theory. You will see now why. You will see now the motivation to do this because we are trying to apply this to especially to ecology and to neuroscience of consciousness, and we have needed to do it in this way. So the second part will be on the one of the main properties of global attractors, which is the internal geometrical description of these sets. And the third part would be some applications to see how rich the application of attractors can be. And I have decided to talk a little bit on cascade systems, and you will see also why I have decided this in this afternoon. So the first thing is that I have been working on attractors for around 30 years. And so, yeah, attractors comes, especially attractors coming from dynamical system defined from partial differential equations or system or of ordinary differential equations. Not only autonomous or more classical partial PDEs, but also non-autonomous PDEs, stochastic PDEs, delay, multivaluate problems. So now the theory in these 45 years, you should know that the theory of attractor has suffered or a lot of development by many groups in many different places of the world. So now we have a very consistent theory of attractors related to dynamical systems coming from PDEs or coming from ODEs or coming from discrete dynamical system as well. So now we have a lot of paper, a lot of contents related to this problem. But even if the theory is very well established in the mathematical world, when you want, we have noticed that when you want to apply this theory to other sciences, as physics, working with physicists, ecologists, biologists, people from economy, neuroscientists, we have noticed that sometimes they are calling attractor to other things that we are not calling attractor as mathematicians, and they are losing because I think the richness of this concept is lost because essentially many people, sometimes maybe also in mathematics, in the mathematical world, many people think that an attractor is something that attracts, but sometimes, but this is not the whole truth of the concept. So let's go a little bit to it. So we will start with, if you want, sorry, if you want to stop me at any point, you can do it without any problem, because I have tried, as Professor Murad have said, to avoid many technicalities so that we can go into the concepts and the motivation of why we are doing this. So you can stop me whenever you want. So let's go again to the talk. So we, from a PDE or a system of ODEs, we will define a family of nonlinear operators from the phase space. The phase space is the space, the space where all the evolution of the problem of the PDEs or the differential equations take place. So all the evolution, all the dynamics are seen in the phase space. Why this is so? The phase space, mathematically, you can define as this this family parametricized by time of nonlinear operators from usually an infinite dimensional phase space, which is called, what we are calling as capital X. The main concept in dynamical system theory for infinite dimensional dynamical systems is this concept of a global attractor that I know that many of you knows, but let me go again to the concept. The global attractor is a compact set in the phase space, so it's something, because we are in infinite dimensional spaces, it's something not very big, which is invariant for the semigroup, in the sense that every trajectory starting in the attractor keeps in the attractor, and everything starting and which allows to go backwards in time, even if we are in a PDE. So invariance properties of the attractor is something as important as the attraction property, which is the third property. So we will say that the global attractor is attracting for the semi-Hausdorff distance, which is written in this final line, in the last line, in this transparency. So the attractor is attracting uniformly every bounded set of the phase space. So we have this object, which essentially has these three properties, which are really, really important. It's not difficult to have, as a consequence of this concept, that the attractor is the maximal invariant set in the phase space. There is no other compact set bigger than the attractor. So the attractor is there can be you can find many other invariants related to the dynamical system. So invariants in that sense. So if you start in that set, you don't you keep in that set for all time. So, but there is many invariants. For instance, a cycle, heteroclinic cycles, of course, an equilibria, any equilibria of the system. All of these are invariants. But the attractor is the compact set, which is the bigger one. So, but it's also the smallest close attracting set. So among all the possible attracting set, this is the small one. There is nothing smaller attracting uniformly every bounded set, as I wrote in the other transparencies. The attractor has another third, a very important property, that is made of all bounded complete solutions. Complete solution means global solutions, solutions that exist not only from time zero to plus infinity, but also exist because of the invariance of attractor. This is why it is so important, this property. Is you can, when you take an initial data in the attractor, you can also define a solution backwards in time to minus infinity, from zero or from t0 to minus infinite. So the set of bounded global solutions in this sense are equivalent to the global attractor. So from the beginning, we could have defined the attractor as this set, as the union of all global complete or global solutions, bounded complete or global solutions. And the fourth property of an attractor is that its structure, its topological geometrical structure, is usually described by invariant, smaller invariants, because we have said that the global attractor is the biggest invariant. The structure of a global attractor is described by invariant subsets and connecting global solutions on this among these invariants. So what this is exactly what we are going to stop in this property, because essentially, how to say, after 40 or 45 or 50 years of research on attractors, at the beginning, 40 years ago, it was very important to say that, look at this PDE. This PDE, we have existing uniqueness of solution with such regularity and blah, 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 and it has an attractor. 40 years ago, this was a very important result. 35 years ago, it was very important also to say that this attractor has finite fractal or house of dimension. That was also a very good point. But now, in these last years, to get another paper with another PDE, another model, and to say that it has a finite dimensional global attractor is not so important. It's not so important. It's important. It's new and probably deserves a publication somewhere. But it's not a surprise. Many models has these properties, as we are going to say now. But what is really difficult is to go into the structure of these sets. What's happening inside these sets? Because these invariants inside the global attractor are usually not attracting. Because we will see, we are not attracting. I say, well, let's go a little bit to understand this what I'm trying to say now. So the main topics in the study of global attractors in these 4 or 5 decades have been existent results, and these are the main authors: finite dimensionality of these sets, internal description or characterization. This is where we are going to stop. Robustness under perturbation of these sets, because so some kind of stability, upper semi-continuity, lower semi-continuity, topological continuity, geometrical continuity, Morse-Smale system. So these kind of results on robustness of attractors, and then many applications to PDEs, ODEs, systems, delays, stochastic, blah, 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 blah. Okay, so these are the main topics in this area of the dynamical system associated to PDEs. But so let me talk a little bit on the informational nature of an attractor. And this is something a little bit new, which is because it's not technical. It's exactly to rethink the concept, not only as you are going to see just now. We can say, or at least we say, that the attractor, a global attractor, has a nature which is essentially intrinsic information, because it's an object that we find, yes, we can say we find in the phase space, which is an abstract formulation. It's an object, a global attractor, which is not the result of a phenomenological experiment. I mean, if you want to apply attractors to a big systems of load-coupled Terra system related to population dynamics, you can see a species, relation between the species, and blah, blah, blah. The attractor will say to you how the species are moving, why are moving, the rate of attraction, where they are not moving. You have a lot of information, but if you go to the countryside, if you have an ecologist, you will not find a global attractor. You will find the species, you will find the relation between them, competition, mutualism, and whatever. You will see many things, but you will not see the attractor. And this is why I'm saying that it's not the result of a phenomenological experiment. But there is something more interesting in a global attractor, is that a global attractor, for many years, I thought that the global attractor was an object that you reach when time goes to plus infinity. Maybe because I was being too full, I didn't notice that the global attractor is not only an object that that appears when time evolves to plus infinity, but it was something much better, that the global attractor was there at time zero from t0 at the beginning of the semi-group. From the beginning, the attractor is there from the beginning. Is not the final step of an evolution in time. The global attractor is there, and this is why it's explaining not only the asymptotic behavior of a system, but also is explaining the transient behavior of a system. Why is that? This is essentially why we are calling an attractor as an information structure, because the phases, other thing, you can't think in the phases. I used to think in the phases space as an scenario where things happens, where trajectories evolve in time. But this is not the truth. When you have a global attractor, in every state in this scenario has a lot of information. Which information? The information that says if this initial state is in the global attractor, this initial state, even if you don't move it, they know what it's going to be all the future of this initial condition, and what is going to be all its past of related to its initial condition. So the initial condition is not something waiting to be moved. The initial condition is something totally full of information of they really know what it has to do, because essentially it is in a landscape, in a transformation of the phase space, which is absolutely transformed in order that you don't have anymore an scenario, but what you really have is a landscape full of information informing the dynamics. I know that this is new, and this is something maybe difficult to understand at the first time you are listening, because it's new. It was also new for me. Let me go to a very simple example, because this idea is the key idea we are trying to explore in order to be useful for other branches of sciences, as I will say later. This is exactly the idea we are trying to develop, not something more technical, but something more conceptual, as I'm trying to do. Look this picture. We have a two-dimensional Lotka-Volterra system. Maybe this is probably this is a cooperative, so two species are in cooperation. So the phase space, because we have two differential equations, the phase space is R2. So R2 is the space where the evolution of trajectories take place. Okay, so it's like an scenario. But this is not what happens. On the left, here, we have a small representation of the structure of the attractor related under some values, of course, of alpha 1, alpha 2, and gamma 2, 1, gamma 1, 2. This is a structure. This is a picture of the structure of the attractor related to this equation, which phase space is R2. But R2, which is a plane, we know it is a plane, because of the existence of this attractor, is transformed into this easy landscape, very easy landscape. And why is it important? Because if you take, for instance, this point, this blue point, or this red point, you will see that this point exactly know what it has to do forwards and backwards in time. And it does many different things because it has to run by this landscape, which is not energy, which is not a species, which is not matter. It's a space of is an informational transformation of the neutral phase space R2. So, but this landscape is there from the beginning. This is why the attractor, I was saying that the landscape is there, the attractor now seen as a landscape is there from the beginning. For instance, let me go a little bit more. This is a small picture of the Lorentz attractor. The Lorentz attractor, you know, is a chaotic attractor, and every trajectory and it has a very high sensibility to initial conditions and blah, blah, blah. But for many years, I was asking myself how a point which is very sensible to a very close point, in the sense that two very close initial conditions are doing many different global trajectories. So you know, in the Lorentz, in any chaotic attractor, initial conditions which start very close evolves in a very different way. But any initial condition, all initial conditions in this Lorentz attractor pictures exactly the same Lorentz attractor. So why trajectories that seems chaotic knows that they have to picture exactly the same chaotic attractor for any initial condition, even if they are close or not? The answer, my answer, I think after these many years thinking in this context, is that the initial conditions doesn't know that they have to picture the Lorentz attractor. They know that they are in a landscape pictured by the Lorentz attractor, and they only have to follow this deformation of the phase space. And because these points, especially in the Lorentz attractors, are recurrent points, so that we are not transient, they are going to all the space, they fill the whole space. At the end, all they are picturing the same fractal set as the Lorentz attractor. I don't know if sorry, I know that we don't have a lot of time, and maybe I'm not explaining very well, but this is a very important idea, what I'm trying to say, even if I'm not explaining as well as I want it. Let's go to the second part, a little bit more quicker. As I said before, one of the main, you can see it here in this picture. In this picture, is very important to understand the dynamics. Is to understand how the attractors looks like, How is the geometrical description of the attractor? So let me say something from the structure of global attractor, which is a part of the studies of this part of dynamical systems. We know what is a Lyapunov function. A Lyapunov function related to a semigroup and related, associated to a finite family. We are going to put it could be infinite, whatever, but a finite family of isolated in the sense that they are by pairs intersection is empty. So suppose we have a finite set of isolated invariant sets, smaller than the attractor. All of these invariants has to be in the attractor because the attractor is the biggest invariant set. So suppose we have a finite set of invariants inside the attractor. We call a Lyapunov function, a function from the phase space into R, which is decreasing in all trajectories and are constant in these invariants. So this seems a very abstract definition, but we have worked on that for many years, and we know how helpful if this is this concept. But behind this concept, there are something very important that we can understand very well how is the dynamics of the semigroup when we have a gradient semigroup in the sense that a semigroup which has a global Lyapunov function. So let me remind you what is the unstable set of an invariant set. The unstable set of an invariant set are the points such that backwards in time we are converging to E. The unstable set of an invariant capital E are the points that backwards in time are converging into E in this sense, backwards in time. Okay, so this is the invariant set. So, but look how interesting is this result related to the structure of attractor. When we have a semigroup which is gradient, the attractor is made by the union of the unstable sets of these invariants. Look, this is probably the most clear result in which you can see that most of the attractors are not attracting because are unstable sets. The unstable set is something that attracting backwards in time, not forward in time, as in the definition of attractor. But the attractor is exactly this union when we have a Lyapunov function. We have something else when we have a Lyapunov function, is that we can order these invariants in the sense that every global solutions, remember that the attractor is the set by the union of the global solutions which are bounded. So every bounded global solution goes backwards in time to one of these sets and go forwards in time to one of these sets. So this is because we have a Lyapunov function. So what I'm trying to say is that the existence of a Lyapunov function has a lot of information on the internal dynamics that we can see on attractor, also on the external, but this is not in this. We can say something else. That we will call an homoclinic structure or heteroclinic cycle in an attractor to a finite collections of invariants such that we start in an invariant, we go to another invariant, we go to another invariant by global solutions, and you finish in the same, in the first invariant. So we make a cycle, but not because we have a periodic solution. We have a cycle because we have heteroclinic connections that starts and finish in the same point. This is what we call an homoclinic structure. So we could prove years ago a very important from this particular area that we are studying, a theorem that says that to have a Lyapunov function is if and only if to have an attractor made by the invariants and connections without heteroclinic cycles or without homoclinic structures. So they are the same. So there is an equivalence between the concept of Lyapunov function and the internal dynamics of the in the attractor. So we can say, but we know from years ago that essentially every global attractor is in this way. We have in any global attractor essentially invariants and connections. So why this, and this is what Norton years ago called the fundamental theorem of dynamical systems. What is the fundamental theorem of dynamical systems? That says that a global attractor is made by the invariant and connections. The connections are gradient points, and inside the invariants we can find recurrent points. Some recurrent points can be chaotic points or chaotic behavior inside the invariants. Okay, so what I'm trying to say is that it's very general that you can also associate a graph, a dynamical graph, not a dynamic, sorry, a graph, but made of inside a graph describing the structure of an attractor. Let's go to the third part. We are going to study now in this last part of this talk non-autonomous equation. When we have a non-autonomous equation, non-autonomous in the sense that the nonlinear term or also the linear term can have time dependence, so that for every time we have that the evolution of your solution is changing the laws of movement. So this makes the study of attractor much more difficult, because now we have several concepts of attractor. The attractor is in an equation, for instance, in an equation like this, you don't have to expect to get any equilibrium point. This doesn't exist anymore. So what is going to be an equilibrium? So if we don't have equilibrium points, so the invariants here are time-dependent sets, not this invariant we are talking about, but because we have no time to give a talk on non-autonomous dynamical systems, we are not going to stop anymore. But what I want to say is that there is everything conceptually are very different when we are in this framework of non-autonomous. But there is one different concept of attractor that I'm going to stop. Let's see what happens to this particular problem. Suppose we have this non-autonomous differential equation in a Banach space, this one, and suppose that the x equation goes into the y equation in this way, so that we have, and the focus, what we want to understand is the y equation, the blue equation. But the blue equation is influenced by the red equation, the x equation, but the blue equation does not influence the x equation. This is a cascade system. And this is a truly non-autonomous, non-trivial, of course, non-autonomous because here, it's not non-autonomous also because it's here. This red equation could be autonomous, not depending on time, the F non-depending on time. But once you go into the blue equation, the y equation, this term makes this equation non-autonomous. So you cannot avoid to work on the framework of non-autonomous dynamical systems. So this is a truly non-trivial, non-autonomous, non-linear partial differential equation in Banach spaces. Why we have to study from, let me say, from some years ago, we are studying with other scientists, not mathematicians. We started years ago, 8 or 9 years ago, starting with neuroscientists, because we are still very interested in how to use mathematics to understand human consciousness, and human consciousness, especially for patients which has deep injuries in their brains. And we are also working with ecologists, which again are not mathematicians, but they are theoretical or computational ecologists. So because of as many times happens, because trying to work with all the people out of the mathematical world, they ask you for some mathematical results that you really don't know. So it's not that mathematics apply to other sciences, that other sciences push mathematics to new results, as we really know in many occasions. So this is why we are now working on cascade systems, essentially for two reasons. For reasons from ecology and reasons from neuroscience. From ecology, because we know in ecological systems there exists what they call the ecological engineers. So there are some species that are able to transform the ecological environment, but the environment that does not affect too much to them. The main example, for instance, to understand quickly, is the castor in a river. But we are even more interested in the second part, in neuroscience. There is something very new in neuroscience related to consciousness and patience, is what is called relational neuroscience, which is essentially how the patient, something with injured in his brains, how important is the personal relationships between this patient for the diagnosis and prognosis of this patient. But how to model a relationship? And because we have done other results, other studies related to mathematical attractors and consciousness, we are in this work at the moment, but we are very happy to try, at least to try to model relationships between relation not only of equations, but relation between these informational fields related to global attractors. But this is another subject. But I just wanted to say why we are studying cascade system, not because we want to study something more technical that nobody has done in the mathematical world, because we are really interested in other problems coming from other sciences, as especially these two we are trying at the moment. So let me show you, and I will finish this here. The kind of a structure, the fantastic kind of a structure we can see in the easiest case of this cascade system. Look, suppose now we are going to put a strong hypothesis. Suppose that this our red equation with x now with set is backwards and forward asymptotically autonomous. So when time goes to plus infinity and when time goes to minus infinity, in the sense that is written there, we will find an autonomous h minus h plus equation. So we make a strong hypothesis, so we avoid non-autonomous in the first equation, but we cannot avoid non-autonomous in the second. So we suppose that these autonomous equations are gradient, in the sense that we have a finite set of, for instance, equilibria, a finite set forward in time of equilibria of these equations. And when we go take one of these equilibria from the red equation, the x equation or the set equation, take one stationary point and put it in the equation for y here. Sorry, put it in the equation for the y. So suppose, again, hypothesis, suppose that this way equation, which is what we really want to understand. We don't want to understand the x, we want to understand the focusing on the y. On the y is our solution, the solution, we want to understand the dynamics. So suppose for every equilibria, we have this equation, which is again in this case is autonomous, because U star is autonomous, and then B, the linear part, and the nonlinear part G are autonomous equations. And suppose that this equation, this partial differential equation, or this equation in the Banach space, is also gradient. Again, a strong hypothesis, in the sense that we have a finite set of equilibria related to the wave equation associated to the U star equilibria of the red equation. Sorry, I know that I hope somebody is following. I don't know. So the main theorem we can prove in this with very strong hypothesis, and it's very difficult to prove, is I can say that this is not trivial. This is a result that which is it's submitted, it's under revision at the moment, but we can say that take the cascade system, take the two equilibria of the red equation, take a global solution of the blue equation, now written in red, of the y equation, then the wave equation, every bounded solution of the wave equation converts to one of the stationary points related to the stationary point of the x equation, and forwards time to another stationary point associated to another stationary point of the red equation. So this is difficult. Let me put it something like this. So actually, what we have in this cascade system, putting almost everything autonomous, but essentially it's non-autonomous because we cannot avoid, is what we get is some kind of network of attractor networks. Imagine how difficult, but how fantastic and how beautiful is the landscape, the informational landscape produced by these particular systems. Is essentially below is something very schematic to know. So the invariants are now the attractors, and these attractors are made by the other invariants, and then we have connections inside these invariants and connections around all the invariants of the attractors. We don't have time, any more time, but this is really a fantastic picture, even if the equations, even if we have two cascade systems, well, I don't have more time. So let me finish. If you want to ask something, some open problems and work in progress we are doing. In ecology, I say applications to ecological engineers. In theory of consciousness, we are trying to apply to what is called relational neuroscience. And related to intrinsic information, we have to go to do a step forward, how to technically measure the level of information of these attractors, and from the mathematics, from the world of mathematics, we have many open problems as well. For instance, a theory of attractor bifurcation, no bifurcation by small invariants, but bifurcation of the whole attractor that we have been working in the last years. For PDEs, one of the more biggest problems is that to know the structure of the attractors, we essentially have no idea how the structure of the attractors for a general PDE is. We have a couple of examples and no more. So there is a big area for research to apply a structure of attractor for PDEs. And we know that these informational fields are time dependent. So essentially, what I have explained today is something static, but we really know, and we are trying to apply this in some biología del desarrollo. I don't know how to say in English, and and because everything is moving, we really know that the transient behavior of dynamical system is as important as the asymptotic behavior of dynamical system. We have focused on asymptotic behavior, but maybe we are noticing that the really important fact is how to describe the transient behavior before the final state at plus infinity, because everything is moving and the final state at plus infinity doesn't exist essentially. Okay, sorry. So thank you very much.
Thank you very much, Jose Antonio, for this very beautiful talk. So now we open the turn for comment, questions, remarks. So if anyone has a question or comment, you can open your microphone and just ask the question to Professor Langa.
I have one question.
Yeah?
Sí.
Go ahead.
Thank you. Muchas gracias.
Yes.
I couldn't be in all the talks, I'm sorry, but thank you very much for your talk. I found very interesting the parts that I saw. And I wanted to ask you, maybe you have said something at the moment that I wasn't, but have you worked with ecological engineers? Or have you done something?
We are trying, we are essentially trying to apply during these months we are working with some engineers on this part from the ecology from these cascade systems. This is the what we but so because the until we are learning at the moment, but what we know at the moment is that nobody has applied try to understand the structure of attractors for cascade system related to ecological engineers. So this is the project. This is the project we are working with some ecologists with the group of ecologists here in Seville. But this is something we are trying to do. But why we are trying to do now with ecological people? Because we needed to understand the mathematical results that we have been working for the last 1 year and a half. So this is the way we are working. So we have this problem. The mathematics needs some developments. Then we go to the mathematics. So a group of mathematicians, essentially with some Brazilians, with Alexander Carvalho, Mateo Bortolam, Maritza, some people, especially from Brazil. We could finish a PhD thesis with a student of Mateo's, Bortolam, and now that we are clear, we are secure of the mathematics we have to use. Now we are going to the applications. This is the history.
Thank you. It takes time sometimes. You have to understand the theory and the
Yes,
to be
yeah,
able
a
to
lot
apply.
of time. Yes,
Yes.
because the result of this result that I only show you the easiest way, because I know that I had no more time. It's very technical. It's totally non-trivial, and yes, the mathemat is not an application of some mathematics that we already knew, but it's something that you have to develop and then try to apply. And
Thank
now
you.
we are in this trying to apply.
Thank you.
So thank you, Johnny. Is there any other question or comment? I have a question, Jose Antonio. Just curiosity. Do you know what you want what you want to represent at the end? I mean, what you want to obtain at the end, or
What
I
you want
mean,
to think in which problem?
for instance, in the application, no, in the ecological problems.
Yes, yes,
So,
yes. You know, once you see the attractor as an information landscape, you have this is probably the more fantastic part of the history, because once you have this object, even with another nature, which is a matter, not energy, is information. intrinsic information, then you can see how to perturb, how to move, how to transform, how to bifurcate this object. So essentially, in the cascade system, you see very clear mathematically. I don't know how far we can go into ecology, but mathematically, you can say very clearly how from outside that things that satisfy the dynamical system, how they infer the dynamics inside of the object you want to study, but infer, but not determine. It's fantastic in the sense that that's a big property of complex systems, because because you have this object, this new object called information structure, information field, that how to move, how things outside can can act inside another system to this level of attractors and not to the level of equations, because we are very used to transform the equations, but we don't have to transform anymore the equations. You can think, and this is why it's so important for the what I call the relational neuroscience, because essentially medical doctors really know that from outside you can change the behavior of a brain without touching the brain directly with chemistry, because the brain, the consciousness probably is more than chemistry. That's a more fantastic thing that goes into other theories of consciousness we are working from years ago, and we are very happy, and it's an honor for us to have found a possibility from mathematics to go into these so deep branches of other part of sciences.
Very interesting. Okay, thank you very much, Jose Antonio.
Un placer, Diego. Muchas gracias por la invitación.
So if there is no other question, so thanks again for your very nice talk, and